Okay, good evening, guys. Tonight, I would like to talk to you about quality of service in IP network, or better, how to support quality of service within an IP network. Let me share the screen with some slides. Now, I would like to start by recapping a bit what we saw in the last class. In the last class, we saw this black box approach. So we basically decided to wear the hat of a multimedia application designer. We consider the network as a black box characterized by delay, jitter, packet losses, and throughput. And we saw mechanisms for coping with the limitations of a network. Now, in this class and in the next ones, so we will start asking ourselves how to design networks but better support multimedia applications. Or, in other words, we are taking the network engineer approach. So, through a quick summary of the last class, we basically saw these four network level key performance indicators. The first one is the one-way delay, and basically we saw that it is a make or break. So in a sense, there is not much you can do as an application designer about the one-way delay. If the delay is too large for your applications to run, well, just forget about your applications. There isn't really much you can do about it. We saw a similar situation happens with the throughput in terms of ability of the network to sustain a multimedia application that requires a given throughput. And we saw basically this GG1 model, which allows us to actually understand quite well what happens. And when we spent a considerable amount of time discussing about jitter, and we saw that the playout buffer is the method for handling jitter. Of course, it comes at a cost. It introduces additional delay. And we saw these two extreme policy, the I policy and the E policy. And we briefly discussed adaptive buffer dimensioning techniques. Last, we discussed about packet losses, and we saw how forward error correction, in particular erasure codes, can actually conceal packet losses. However, they require careful dimensioning. And also here there is a trade-off because we increase bandwidth and the delay by basically achieving a lower packet error loss. Okay, the fundamental notion of today is the one of quality of service. It is not actually class 31 that you should be looking for, but the one of last week in which we discussed about quality of multimedia. So, we all know that IP is based on best effort. In an IP network, all packets are treated the same. There is no difference between packets belonging to different applications. And the routers cannot actually distinguish between packets that come from different applications. This paradigm, what we also call the end-to-end paradigm, is one of the reasons of the fundamental success of the internet. The fact that basically, by taking this approach, we can have IP running on top of every network, and we can have every application running on top of IP. Plus, we have this very small wrist in that IP provides a very limited set of functionality and APIs. Of course, this fact that all packets are treated the same are also limitations for multimedia. Now, of course, some of you may wonder whether it is a real limitation, and that in our daily life, we all use a lot of multimedia applications. We use Skype, Hangouts, we watch YouTube videos, and so on and so forth. So even if we have the feeling as users that everything is going right, well, in a sense, it's because what we are doing is that we are just over-provisioning the network. So we are providing bandwidth in excess, so that still, despite the limitations of IP, we are still able to run smoothly multimedia application. However, this might change in the future. And that is why it is important to understand how to, in a sense, cheat IP networks to support quality of service. There are 4 principles for quality of service that we will see tonight. So, we will be using in this class and in the next one this very simple butterfly network that you see on the bottom of the figure. So we basically have 2 connections. The red one that links host H1 to host H3, and the blue one that links host H2 to link to host H4. And what is interesting is that this connection actually shares a link, the link between router 1 and router 2. And besides sharing the link, they also share this output interface queue of router 1, which is the buffer that basically packets of both connections share before being forwarded to router R2. And we will assume that the link between the 2 routers has a capacity of 1.5 megabit per second. So let's start by considering a situation in which the red connection is actually a multimedia one. In this case, a very simple voice over IP connection. And the other one, the blue one, is a pure data connection, a file transfer actually. So that basically we have these 2 connections, one multimedia and one data, that share this common link. And of course, you know that FTP runs on top of TCP. It uses TCP as transport protocol, and TCP has this bursty behavior. So FTP can actually create bursts that can congest the router, causing audio losses and delay for the voice traffic. And in this situation, what we would like to do was to actually give some form of priority to audio over FTP. Because, well, in a sense, we know that FTP is not really sensitive to delays. So if you download a large file, the fact that it takes 1 hour or 1 hour and 3 minutes, well, you hardly notice the difference. But if we add delays to the voice over IP call, well, this is something which might actually disrupt the quality of experience as perceived by the end users. So the first principle is that if we want to somehow differentiate between the 2 flows, we need to be able to distinguish them, which seems obvious, but it's actually not so obvious in the IP world. So what we need is some form of packet marking. So we need to mark packets to add something which allow the routers along the path to distinguish them and potentially to treat them differently. And where do we need to do it? Well, we actually want to do it at the moment where the packets enter the core network, what are called edge routers. Plus, of course, once we have the packet marked, we want the routers to treat them differently. But we will see this in the next class. So the second problem that we might face is that actually we might have a situation in which, sorry, something went wrong here with the video. Something in which basically one of the two flows is misbehaving. What do I mean by misbehaving? By misbehaving, I mean that basically this flow declared a given bandwidth, let's say 1 megabit per second, and then it's trying to push more into the network. And of course, if it tries to push more, that might actually can cause problems for the overflows. So what we want to have is what is called packet policing. So we want a way to force the source to actually stick to the characteristics, typically in terms of bandwidth, that it declared when joining the network. And where do we do it? Well, of course, we want to do it before the packets get into the network. So again, we do it at the network edge. And this is fundamental, is that it provides protection in terms of isolation for one class from the others. Now, of course, once we have understood marking and policing, well, we would be tempted to go back to the virtual circuits, right? So we basically create virtual circuits. So instead of having this shared buffer, we just create two different buffers. They can be just logical. They don't need to actually be physically separated. And basically, we have one logical link for the red connection and one logical link for the blue connection. Everybody is happy, apparently. But in reality, what we are doing is that we are wasting bandwidth. Why are we wasting bandwidth? Well, because, for example, we know that voice conversations have this talk-spurt structure. So typically, there are intervals in which I speak, so basically I generate traffic, and then I listen, so I'm not generating traffic. And if when I am not speaking and not generating any traffic, the bandwidth is reserved, well, I'm just wasting bandwidth, and bandwidth, of course, has a cost. So it is true that we want to provide isolation. This was principle number 2. But still, we would like to use the resources as efficiently as possible. And then there is this, basic fact of life, that of course the network cannot support traffic that goes beyond its capacity. So what we would like to do is to have some form of admission. So that basically a flow declares what it needs from the network, and the network decides whether to accept the call, to admit the call, or to block it. And what is important here to note is that we are, in this, with this principle, putting intelligence back into the network. Because here, it is actually the network itself that can actually take an action, such as denying a call to join the system. So, summarizing, we have these 4 principles for quality of service over communication networks: packet classification and marking, isolation, policing and scheduling, high resource utilization, and call admission. And in the next class, we will be looking at the mechanisms for achieving this. So that was it for the class of tonight. The next one, we will discuss some of the mechanisms, in particular in terms of scheduling policies for supporting quality of services over IP networks. Talk to you soon.